Check it out now, y'all.
nanoHUB-U online instruction.
Hi, this is lecture 4.2. This week we're talking about interfacial relationships. And today we're talking about additional reactions besides those reversible reactions that are occurring in a battery. As we have been discussing before, one of the most important things, if not the most important thing occurring in the battery, occurs right at the interface. This is a very interesting micrograph that Kang and Sater published in the Nature paper in 2009. You can actually resolve the atoms. Here you can see here the different layers of what occurs in the system. And here you can see at 5 nanometers for this particle of material, how there's a transition zone and there's other things going on in the battery. Okay, and of course with that they propose that they can have very, very large C rates, in this case for the lithium iron phosphate system. While the results may be controversial or not, okay, clearly what occurs at the interface is what's controlling that large C rate that the battery has. Okay, and if you still can't see it, right, basically this is the core of the particle. Okay, and this 2.5, maybe 3, maybe 4 nanometer region, that's the interface. That's where all the action occurs. Okay, and if this reaction rate is very slow, basically we'll be filling in this particle very slowly. But if you increase the C rate or the reaction rate, the Buchler-Böhmer reaction at the interface is very high, then we will pile up a lot of material right here at the interface, inducing with that these concentration gradients in the system. Okay, this becomes very important because clearly if I manage to reach the solubility limit of my particle right at the interface, okay, even though the core of the particle can have a lot of lithium available for transport, the particle will stop accepting lithium ion. It's just the equivalent of, I guess, of going into a party and you cannot get into the kitchen of the house because basically everyone's sitting right outside and so you cannot even get in. Okay, so if everyone's just in here and they don't distribute it evenly in the house, you really cannot get to where the goodies are. Okay, so in the same way, okay, you really want to be able to have matching reaction rates so that the rate of transport to the core is balanced by the rate of interfacial reactions, and something we haven't talked about is the rate at which lithium is coming from the outside right into that surface. What occurs at the electrolyte is very important too. And well, I'm just going to summarize a few organic electrolytes. Okay, it's really a zoo out there of how many electrolytes they have. Here, for example, you have EC and PC, which are two of the most main used electrolytes these days in lithium-ion batteries. Usually what you do is you don't use them by themselves. You mix them, for example, in this case, EC sometimes is mixed with DMC or DEC. Also another one that is used a lot is EMC. Each of them have different contributions and they give you different amount of transfer rates, in this case different transport, or different conductivities or different diffusivities, if you may. This becomes really important because well, here in this case I'm showing you also the melting points and boiling points. Notice that the ranges end up being very short, and actually that's why you end up playing with different mixtures, because for example you can see that if you are above 36.4, where they will start melting, and above 248 they basically will start boiling. You certainly don't want that. Okay, and each of them, of course, as being organic electrolytes, they can also catch fire and can be a problem also when you use these batteries. There's a whole range. Now, you don't use these electrolytes by themselves. Typically what you do is you mix them with some salts. In this case, these are some of the most used salts. LiPF6 is one of the most used ones. The same as LiClO4. Typically you mix them with some of the ones I told you in the previous slide. And there are many reasons why people use different types of salts. In some cases they use them obviously to transport the lithium ions from one side of the electrode to the other one. In some cases they use them to stabilize the system and to inhibit some side reactions that may occur. Okay, and in the same way, right, and well, you can see here how they made a point on how is some properties in certain electrolytes, in this case ECDMC being one of the ones most used. Okay, well, here's another one, PC. Now, again, these electrolytes are not being used in isolation, they're usually used in mixtures. And when you use that, what happens, for example, you have here an isopath of EC, DMC, and PC. And notice that what happens as you change the different fractions of them, you will induce different phases within the mixture, with the possibility of precipitating some of these phases, which could have low conductivity, and with that basically induce low properties in the system. And in this case, you can see how, as that happens, in this pseudo-binary diagram of the EC-DMC diagram, how if I go below 10 degrees centigrade, say in this case 4.9 degrees, you could actually form a solid liquid mixture that basically in this case the mixture will crystallize, providing me with a set of obstacles around which the ions will have to to flow. Now, this is just in the electrolyte, and these reactions, bulk reactions by themselves, can slow down the transport of lithium in the cell. Now, at the interface, which is the part we're the most interested in, as this electrolyte is coming here, you can see the giant molecule coming. What you really want, the desired reaction, is you want the lithium dissolved in the electrolyte to basically intercalate here. Okay? What happens actually, specifically in the anode, in this case, a carbon or graphite particle, what happens is that in some cases, some of these electrons are being exuded as part of the reaction, inducing with that local interfacial polymerization of products that you don't necessarily want. For example, this Li2CO3, this lithium carbonate actually forms also the interface, as well as any with the salts themselves, forming with this a passive thick layer. Think of it as a crust of several nanometers that actually forms right at the interface. You would think that this interface, this layer is something that is undesirable, but it turns out that without the appearance of this interface, we wouldn't be able to have a battery at all, because that allows you to specify an overpotential that will drive, as we have discussed in the previous lecture, lithium and electrons reaction into the particle. Okay, so that becomes very important in this case, and because there's so many things going on in this interface, there's so many different types of chemicals. It's referred to, all our ignorance is basically summarized in this by calling it the solid electrolyte interface, or if you prefer, it's referred to as the SEI layer. Okay. Now, what is in that that layer? It's again, this is another topic of a lot of things going on, a lot of research. There are so many chemicals going on in there. In this case, you have, for example, in the first line, you have this complex hydrocarbon that has lithium in it as a result of the reduction of ethylene carbonate with EC-based electrolytes. In other cases, you have, for example, PC, which occurs, of course, you put in the electrolytes, mixing with the materials outside. The electrode, the lithium carbonate that we discussed, sometimes occurs, sometimes it doesn't, but it becomes important. Some of these could be very detrimental to people's health, for example, because it could be very acidic. And well, as you see this list, you can see that it's many of them actually cluster in different regions, making it really this interface a very complex object. Now, very recently, there were some experimental measurements of what actually occurs at this interface. Turns out that if you're, in this case, what you have here is the depth profile of the intensity of a certain chemical as a function of thickness of the SEI layer. For different components, in this case you have a B+, okay, occurring in the system after 30 minutes, 3 minutes, and 15 minutes. Okay, and what people find is actually the SEI layer very close to the surface is very dense, and as you get away from it, it becomes more and more porous, suggesting really that the lithium ions are basically besides going through this very large porous network of particles, when they get here, when the lithium ions get here, they have to traverse this local nanoporous region where they end up reacting up here very, very close in this 5 nanometer region. That density, that dense structure basically specifies something much more complex than we thought. Now, in this case, you can see that depending on how it was created, you can see that you have the B plus ions over here, and the lithium oxide ions, how it's actually depleted here, goes through a maximum and then goes down to a baseline level, really suggesting that all the action is occurring in this area, and then down here where it's much porous, it's really just a buffer zone where material is coming here in order to react. Okay. If you do this for different C rates, what you find, for different C rates, for different instances, you can see that after 0 seconds or 3 minutes, basically you have here a very homogeneous layer, but after 15 minutes, you really end up having the profile that we were discussing, really suggesting that this interface is not as unstructured as one thinks, but there's a lot of things going on in the through thickness basis. Now, if instead of looking at it through the thickness, we look at it from the top, what you will find is that actually, as you look at the different components, you have, for example, the B plus ions, the Cl minus, and the Li2O plus. You can see how it inhomogeneously distributes throughout the surface of the anode material, imposing with that basically regions where you could have high reactivity versus regions that have not such a high reactivity. And well, people have also looked at in much more detail, and well, you can see here a much more accurate picture with that mess of reactions going on. And how some regions look very hilly, others have a large depletion, and this becomes very important when one discharges a battery. Why? Because, say for example, the moment, of course, you put your anode into the electrolyte, say if you put a pure lithium metal in it, what you will find immediately an SEI layer will form. Okay, that's of course that's a flat surface. If it's instead a curved surface, what you will find is that it will form this dome-like shape, and as the material deposits, the lithium actually starts to grow. Okay, but again, this SEI layer, because of its complex morphology and chemistry, can be actually very brittle, and when that happens, usually what happens is that it could open up some gaps. Okay, and at least that's what is hypothesized. Changing the homogeneity of that reaction, favoring some regions for react with respect to others, and the crust, the SEI layer crust, will allow easier diffusion through the open areas, and as a result of that, it is expected to be a mechanism for the anisotropic growth of this lithium material, making then instead of growing flat, it'll start just growing in these very complex shapes that are usually called dendrites. So when you are charging your cell, okay, what you will find is you will have these giant boulders that they form as a result of a combination of the breaking and redeposition of SEI, which people expect to happen. Now, if instead of recharging your cell, you're discharging it, you will see the opposite. Basically, ideally, you would want that SEI layer to deposit uniformly and that the lithium metal to grow flat in every direction. Instead, what you find, okay, is that when you are dissolving it, you will end up inducing these little depressions that will make these corners more likely to be stable with respect to those. So basically, that will force that cavity to come further down and the SEI layer to break. And as a result of that, basically you can develop pinching or to develop other regions with other reactants that you really don't want there. Now, this is observed, experimentally it's observed that then you will have these valleys, and so after several charging-discharger cycles, you can think of having some regions that will have these giant buildings of lithium accumulated, while other regions you will have these giant valleys or depressions. completely changing the efficiency of the reaction, and this is also detrimental for the performance of the cell. Now, there are other things that SEI or these interfacial reactions do. Okay, as SEI forms at the interface, in some cases, the molecules of SEI, as they sit in front of the graphite interface, some of them have such a large driving force that some of them end up getting inside the lattice of the lattice, opening up further the lattice, and in some cases completely breaking it. And as a result, you can see these surface layers of graphite basically exfoliating into the electrolyte, losing with that some capacity and impacting the overall response of the system. And you can see here in these micrographs how the material before being used, how it looks very nice and pristine, and after sometimes you can see how all these blisters have formed and how the material is basically losing charge as it's all redissolving in the electrolyte. Now, what are the reactions that we find occur in the system? If we should summarize them, first, of course, you have the formation of SEI simply by taking our particle of anode materials and dunking it into the electrolyte. Okay, as a result of that, this layer forms. This layer is very important. We want it to form, but we don't want it to keep growing. If this layer is forms and it's stable, if you have a stable SEI, you can actually reversibly charge and discharge your cell. If it keeps growing, the interfacial impedance that it will form will actually preclude the battery from charging or discharging, especially those particles who have a thick SEI. Okay, and as it happens, okay, well, again, you want it to stabilize. If it becomes very thick, then nothing will come in here and you will be able to use it. Now, if on top of that, you start basically spalling or dissolving SEI and precipitating it, you will lose some of your active material, the quality of your electrolyte will degrade, okay, and this will effectively impact on the performance of the cell, at least on the anode side. Now, if instead you start plating right at the interface, that could lead to corrosion. That could lead, if this dendrite touches the counter electrode, that will induce an internal short circuit, killing effectively your battery, and and even if it doesn't do that, the plating and subsequent corrosion could completely kill your cell. So I guess the moral to the story is that you want the formation of a stable SEI layer and the avoidance of these side reactions as they occur. Now, as we discussed several weeks back, this graphite layer was used effectively to not allow the formation of these arborescent structures of lithium. So, but you can always push the discharge or recharge rate to induce their formation. Just to show you the complexity of what's going on in the interface, all these reactions that we've just been discussing, for example, you can see electrolyte decomposition. What does that induce? It induces the loss of lithium and the rise of impedance, and that of course will induce capacity fade or power fade. And as we were discussing, the stable formation of SEI with additives will make the battery last longer. If you have the solvent co-intercalates, and you can also form gas in your cell, what will happen is that you will develop loss of active material and of course capacity fade. Okay. If you decrease the accessible surface area due to continuous SEI growth, that will also raise impedance and the potential of your cell will drop. If you induce changes in porosity due to these volume changes or SEI blockage, then that will also raise impedance and your power will drop as well. If you lose contact between active material due to volume changes during cycling, that will also induce loss of active. Basically, you can see how every single thing that you do, if it deviates from an irreversible charge-discharge cycle, will lead to capacity fade and to power fade. And actually, these list of possibilities is what controlling effectively the long-term lifetime of your system. You might not notice this on one specific cycle, but it's until you cycle it for hundreds, sometimes thousands of cycles, well, you will start the occurrence of these things, including the cell bloating, including even if it doesn't bloat, how the power density just keeps dropping. Okay, from all of those, clearly these that you have over here, electrolyte decomposition, decrease of accessible surface area, and changes in porosity due to volume changes, all of them you can see can be fixed by simply forming a stable SEI. So formation of a stable SEI, it's actually one of the key fields that are right now being studied, because what you want is for that SEI to basically form and stay pinned so that nothing really will happen. Now, that's what occurs in the anode side. The cathode side of the equation is not, it's also undergoing some things. Here's just a slide summarizing, for example, what occurs in the lithium cobalt nickel oxide system. Typically, when you have your battery particle, if you start actually cycling your cell, if you start putting other species in it, you can actually evolve your material from a layered structure, which is usually what you want, to a rock salt type where basically ions are very hard to diffuse through. And that is bad because that basically decreases the diffusivity and drops the performance of that cell. Okay, and again, typically when this happens, these organic solvents may lead to oxidation, transesterification, and polymerization that could actually completely kill also the interfacial reactions. In some cases, some of this cathode material will effectively dissolve in the electrolyte and sometimes even diffuse all the way into the anode, leading to instabilities in the SEI and poor response of the system. Okay, this is again for the lithium cobalt nickel oxide system. For the lithium manganese oxide, you can see something very similar occurs. So you can see here how you can induce HF evolution in the electrolyte as the LiPF6 and the different components of the cell react with the manganese in the electrolyte, which allows you to basically precipitate this component, which could migrate all the way into the negative electrode, inducing a drop in performance. Finally, this just summarizes all the possible cathode reactions, at least some of them. Clearly, you want these particles to be in contact with the surroundings. So if you have that conduction into the particles drop as a result of the binder decomposition, that will drop the performance. If you lose contact of your particles with the electrolyte and the conductive phase, that will also lose to drop in performance. If you reprecipitate or form new phases, that will also lead to a loss in performance. Or if the electrolyte decomposes as a result of reacting with the particles, that will lead to a drop in performance and the formation of gas, which may actually eventually make your battery also fail. Okay, now this is all interfacial reactions, they occur. One of the most important problems that happens in a rechargeable battery is the formation of dendrites. So in the next lecture, I will be talking about dendrite formation alone. Okay, thank you.